Welcome back. See that our offline audience is going strong so far. So we're going to continue on the fourth lecture.
Well, thank you. Thank you for the offline and online audience. Okay, so first I have to say apology for those who did try to do things last night by themselves, because I did not say a couple of things which you would need to solve at the finish group. So
yeah, I feel it.
Okay. Well, so my apologies. I realized when I was basically prepping for today. Okay, so first of all, let's recall what we will need. So we need Buk's lemma. Buk's theorem. Buk's. It was following. We had polynomials. S. S. And the variety which they cut out. Zero, and the statement which we said was that if it's zero dimensional, then it's a finite set of points, and for the cardinality of that set was bounded by the product of the degrees. It's fine, but we will also need a slightly more general statement, which is when dimension is not zero, because we'll need to just make that. I just forget to mention that. So furthermore, if I'm looking at the zero set of any number of these polynomials, this variety, so this is a variety. It might not be reducible. I mean, for example, this polynomial might be x squared minus 1, and this polynomial. We saw the example, but it can be written as a union of small number of irreducible varieties. Can be written as a union of few, and few again, it's product of the degrees irreducible. Again, intuition is still basically the same as before. Again, imagine you have, say, two collections of hyperplanes in free space. You intersect them, you get an intersection of lines. This is basically the extremal example. All right. So that we will need that. And another thing which they will not fall farther. Another statement we will need. This is basically Hilbert's Northstall what is the form of it? Is that if the dimension of variety is non-zero, positive, then W contains infinite elements. And again, just to remind you, we define varieties as set of solutions over algebraically closed, which is why we actually can find infinitely many points. If you request more, talking about the solutions over the finite field again. Okay, so that's all. Okay, so now let's prove for every S there is C, to basically about S to the power S, such that the extremal number of the KST is power. We've got it, we have a graph which I as we mentioned before. On the right, we have Q to the S. On the left, we have Q to the S vortices. Oh, sorry. Sorry, I'm still doing the slightly easier version of the Zarankiewicz. Sorry, we will prove this, but this is the Zarankiewicz warm-up. Warm-up, then we'll upgrade it to this statement. So remember, Zarankiewicz warm-up means we actually going to be forbidding KST, S on the left and T on the right. Okay, not both. So we have Q to the S vortices on the right, FQ, so which is FQ to the S, and just Q to the S vortices on the left. And for each vortex on the left, we chose a polynomial. So there is, so D is going to be the parameter which will basically be about S squared. And we're going to, for each vertex V, we're going to pick a polynomial F sub B of degree at modulus D uniformly.
This V means as long
Sorry?
as tuple.
Sorry?
So what is the V?
What is
V?
so again, so for example, we have Q to S vortex on the left. We have vortex, and to each vortex we associate a polynomial. So and now I'm the graph will be the V will be connected to the zero set of this polynomial. So the edges from V to A, so V on the left, A on the right, if this polynomial vanishes. I mean, if you prefer to think about it, my vortices are just polynomials, right? And I'm just connecting polynomial to its zero set, okay? Except when I'm doing sampling, I might accidentally sample the same polynomial twice. It's very unlikely, but for analysis, it's just going to be easier not to worry about it.
Inside of the construction, can you finish it?
Yes. So yeah. So basically, this is construction for every Q, which is prime power, and and Q. You can take Q to go to infinity, and therefore obtain larger and larger constructions. Okay. Okay. So this is now let's analyze this. So, well, let's yes, we do pick up the edge. Okay, and we do that. Then finally we do the usual thing, and for each KST in this graph, remove one edge to kill it. Okay. So this usual division argument. So we have this construction. It might not be good because we might be very unlucky with our choices, but we're just going to remove one edge from each bad KST, and then we are going to clearly get a KST tree graph. And now the only question is, how big is this KST?
After BA is zero.
Sorry?
If after BA is zero.
F.
The first line of the edge.
One edge.
Because they define the edge.
Ah, sorry. If
Yeah.
F was, yes, thank you. Thank you, zero. Okay, so let's analyze the construction. So first of all, how many edges is going to what? How many vertices it has? Number of vertices. It's clearly 2 to the q to the s. Number of edges before deletion. Well, it's easy to compute in the expectation, right? It's the total number of pairs, which is q to the 2s, like that, q to the s versus here, q to the s versus here, times probability that if I take the random polynomial evaluated at some point A is going to get 0. Probability that is 1 over q, because it's just that argument we spoke, that pick all the coefficients except the constant coefficient, and then there's only one choice for the exactly one choice for constant coefficient, which will make it 0. So this is times 1 over q, and this is exactly the number of vertices to the power. So this is the q to the s to the power 2 to the 1 minus s plus times the constant. The constant is a constant, which is raising this to some power. Okay, so so number of edges before deletions is good. So now we only need to argue we're not going to delete many edges. Or in other words, we need to estimate probability that at a given place you're going to have a KST. So let's do it. So let's pick S distinct vertices, B1, Bs, and we are interested in the neighborhood, common neighborhood of these vertices. Well, so common neighborhood will be essentially the following set. Okay, so not quite. I'll say the difference. So it's going to be a set of all those A's. Like I'm leaving space here intentionally. A set of all those A's, so that f first polynomial is 0, second polynomial is 0. All of these polynomials 0 at that point. Sorry. At that point. Okay. Yes. Right. Right. So what I'm interested in are the A's which are in here, those the FQ and FQ to the S, but I to use my algebra, I'm going to actually look at the full variety, which is this. Okay. And so if this variety happens to be zero dimensional, if dimension of W is 0, and again, we expect usually its dimension to be 0. Okay, that's just intuition, because each of these equations finds me some kind of hypersurface, and we expect, it should be unlikely that we are going to not get the right dimension. Okay? Each time it's like in linear system equations. Each time we add an equation, dimension should drop unless some kind of linear dependence happens. Except now it's not linear dependence; it's a more general kind of dependence, but the same idea. So we expect this to happen most of the time, and then Bezout. The size of W would be at most, well, the product of degrees of this polynomial, and each of them is d. We haven't chosen it, but we will shortly. D to the power s, and so there is no KST with this as vertices on the left. If we choose T to be D to the S plus. So this will be eventually our choice.
So you're assuming that T is a very large.
I'm going to choose T to be D and this number. Just one more and this is enough. Yeah. So the choices will be, this will be basically slightly more than S squared. We will see from proof this is what we need to take. To say 2 times S squared will be enough. And T will be this D to the S plus 1. Okay, so if you want to write it now, this will be enough. I mean, we'll see from the book. This is what actually S squared plus 1 maybe or something. Okay. Okay, so this is a good case. We need to estimate probability that of a bad case. To do that, we are going to look at 0 sets of a few of these polynomials and ask, what's its dimension? So, let's say Wi to be the variety cut by just first I of this polynomials. And we want to estimate the probability of a piece of I that this Wi has too large of a dimension. So dimension I is more than S. Okay, right. We have we have I equations. So in S-dimensional space, again, by our linear algebra intuition, we expect this to have codimension I. So in ours, dimension S minus I most of the time. And this is the bad event. This is the event that dimension is too large. We want to upper bound this probability. Okay. So let's see. Okay, first of all, P of 0 is 0, right? We have no equations. If we have full dimensional space, nothing is trivial. Everything is trivial. So let's do the induction. Suppose we already know that the Wi is of good dimension. What's the probability? It's okay. So suppose the dimension of Wi is good, and we want to estimate what's the likelihood of adding one equation not dropping the dimension. Okay, Well, we are going to break this variety into reducible components, right? Bizou, which is down here, says that we can write Wi as the big union, let's call it Wij over some bunch of j's, where j ranges over some number which I'll call maybe let's call it t sub j, t sub I, sorry, some t sub I, where the number of these components t sub I is no more than the product of the degrees of these polynomials. This is the L, let's say L less than I, and this is equals to, well, less than or equal than d to the power. Again, this is by the furthermore part of this Bizou. So we have a few of this. Now, let's look at the following. So we have now, if I add one equation, well, I'm going to get Wi plus 1, which is going to be equal to the intersection of the Wi with the zero set of the new polynomial. So I'm being two. So this is a set of all days, but this is, yeah. So that's, I'm adding another constraint. So this is, of course, just I'm intersecting with each of these components, Wij intersect this is zero. Okay, so I have some, this is the intersection again over all j. So now I have a bunch of pieces. So as I have my variety, which is broken into a bunch of very simple pieces. I'm intersecting each of this piece with this new hypersurface. I'm asking, what's the dimension of this? Well, what's the probability that the dimension of Wi plus 1 is bad? This is equals, of course, the probability of the dimension I plus 1 I, right? So again, okay, so I should I'm assuming the, I mean, I'm supposing this, I should write conditional probabilities.
Well, what if the dimension of Wi is smaller than this?
Huh?
I think it is possible because I think we have a degenerate.
So first of all, what I'm writing is still true in a sense that okay, I'm assuming probability this dimension is at most this much. Okay, and I'm asking like what's probability that this dimension is too large? And the only way this can happen is that if the dimension of this is definitely no bigger than dimension of this. If this is no more than s minus 1 and this is bigger than si minus plus 1, this is the only way it can happen. So this is the only thing, this is the only case I need to consider. But to answer your question, the intersection might be empty. For example, if you have two parallel lines,
Yeah.
right? This is what you're thinking. But this is basically the only thing which can go wrong, because if we were doing algebraic geometry class here instead of combinatorics, we would be working projectively. This is definitely everything becomes much nicer. And when you work projectively, you cannot have degenerate intersections, turns out. If you take dimension cannot drop more than expected. Okay, if you work projectively, the parallel lines will midpoint infinity, but it's also true for more complicated varieties and lines as well. But for us, we don't care about it because again, this is the only thing we need to work. Okay, so what's the likelihood that the dimension does not drop as we add this as one more equation? Well, it's at most again by union bound probability that one of those pieces will have too large of a dimension, right? Because this WI plus 1 is the union of these pieces, and we are basically looking at the upper union bound. It's at most the J at most T to I probability that dimension of one of those pieces WI J intersect A F I plus 1 A equals 0. So this thing is, I mean, since it's going to be this not drop, it's going to be the same as dimension of WI J, and again conditional. If dimensions of each of these pieces is strictly smaller than if dimension of each of these intersections is strictly smaller than the dimension of this WI J, dimension of WI plus 1 will be strictly less than dimension of WI. Okay, so this is upper bound, this is union bound. Okay, now remember that this thing was irreducible. So the only way dimension can stay same, right? Remember, dimension was defined as the longest chain of irreducible varieties. Starting from this, you could go to the empty set. The only way this chain does not get shorter if this intersection is the same, because this is irreducible. There's nothing smaller inside which is irreducible the same dimension. So this is literally the same thing as the probability that this Wij is contained in here. So again, by irreducibility. So this is by irreducibility. This is by union. Okay. So what's the probability that f I plus 1 vanishes on all of the points of the Wij? Well, this is here where we are going to use this Nullstellensatz, which I wrote here. This is this lemma. So since Wij contains many points, so okay, since Wij is of dimension of this one, right? There are T plus 1 distinct points. Many, but I only distinct points of Wij. Say Pij1 j plus 1. Okay, so a bunch of points, and so these are points on. And by the lemma, which we proved on the last lecture, the probability that a random polynomial vanishes at a bunch of distinct points, probability that f random f of degree of d d this one equal to 0 for all L 1. That's at most 1 over q to the power d.
Sorry, why every Lij is of dimension at this point?
Oh, we are trying to okay. Okay, you are right. Yes, I need to. Okay, I can ignore those with dimension 0. That's probably what I should have said, right? They're not, because really I'm trying to estimate the probability that this dimension is too large. It's too large. Probability of the W plus 1 is s minus I. My I, right, is at most s minus 1. So this is a dimension 1 or larger. So I'm trying to estimate probability that my dimension is going to be 1 or larger. So, okay, but depending on the value of I, it's some number. So I'm only going to care about the components of dimension at least 1. Well, so let me just here what I should be doing, and you are right, I should be restricting myself only to the components whose dimension is bad. Because the other components which have a dimension already lower than that, I can ignore. Okay. Yeah, so I should be doing sum over this, and similarly. Yes. Thank you. Okay. So probability is very small. Probability that we are going to, or f will going to vanish on and all of these points, and of course, is small. And of course, this is of course upper bound probability that f will vanish on this component. So therefore, that expression depends this thing is going to be at most the number of components Ti times this probability. Now this is small. It depends only on d. So this is just d to the. Let me just write d to the s. It's actually most d to the I, but let's be generous. This is small. So this does not depend on q, right? And d is approximately s squared. So this is just a constant depending on s. It's just a number. Q goes to infinity. So this is going to be, this is tiny. Okay. Now what's our probability? Pi, have probability of the bad event. So the probability that we are having a problem at the step I plus 1, well, it's a probability at most probability we had this problem already by step I plus the probability we messed up the step I plus 1. Okay, and well, since all of the, so since each time we're adding the same quantity, This is just at most I times ds q to the minus d, which is by induction on I plus 1. Yeah. Okay. So now we have our union bound on probability of something going wrong, and it's a good upper bound. Yes. So boom, boom, boom. Let's see. I've already used this lemma, so we don't need it. Let's do it. So probability that there exist S vortices this thing such that the dimension of the variety which they which they cut out yeah. That's V1. V1. The probability, the dimension of this is bigger than 0, so there's bad S tuple. Well, it's going to get most number of ways to choose this S vortices, right? Our graph has Q to the S vortices on the left, so this is Q to the S choose S ways to choose this S tuple of vortices. For each of them, we are interested in probability in P times P sub D, right? So it's going to be D times Q times D to the power S, that's the bound down there, times Q to the minus D minus. So that's our union bound. Big union. Sure. Oh, I'm sorry, I should say, because we're doing deletion, I should write expectation, right? This is expected number of, okay, it's the same thing, right? Expected number of bad X tuples. Because we're doing deletion, we need actually expectation for this. So for each S tuple probability is this one. Okay, this is at most Q to the S squared D so this not D, this is S because we're doing up to S, so I'm sorry. S D to the S, so this I'm just constant depending on S, and I might be choosing our D something like S squared. So squared I chose say, and this is happily goes to 0 very rapid. And particular, it doesn't make any real change for our deletion. Okay, so this finishes the proof of this Zermkevich watermark. Okay, right? We have constructed the graph which doesn't contain KST, S on the left, T on the right, and it has the right number. Okay, I hear people doing. So let's maybe take a short break, and after that we will upgrade this Zermkevich warm up to the real thing. Discuss how to get something sharpness for the partial to run in general, and then maybe see another application of this kind of randomized. Okay, donut time. Thank you. During the break, it was pointed to me that I made a mistake down here because this is the expected number of bad S tuples, but this is not the same thing as expected number of edges you need to delete in order to kill all the bad KST, because a bad S tuple, I need to delete many edges to kill all the things coming from this bad S tuple. So, but it's not that many. It's I just need to multiply by Q to the S. So let me just maybe write it. So and so expected number of edges to delete I can just basically take one of the vertices of this S tuple and delete all the edges from emanating from that vertex, for example. It's at most Q to the S times the expected number of this bed tuples BS. So this is at most this thing. Square times Q to this, and again, this still kills this little thing. So good. So let me now say how we upgrade this warm up to a cool thing. So a cool thing means we actually want a graph where we're forbidding not just S vertices on the left and T on the right, but we're also forbidding the other way around, S on the right and T on the left. And currently our construction is asymmetric because we're treating left and right different. So the way to do that is to modify our construction, obviously, make it symmetric. So this bound. Okay, so I will skip all it. I'll say what we need to modify in the proof we just saw. We are going we're going to have graph with both parts are now S-dimensional vector space over FQ. And we're going to pick a single polynomial, but now it's polynomial in two sets of variables. So there are, I'll think about the variables on the left. I'll call it, X. So X is X is a vector, X1, XS, and the points on Y. Basically, I would use variable Y to refer to that. So this is also a vector, and I'm going to pick a random vector of which is of degree at most in each of the X and Y. So I'm going to pick F. Okay, so let me just try this. It's going to be of the form C, some constants, C alpha beta, X to the alpha, Y to the beta, where the alpha and beta are the multi-indices which are at most. So this is, so so as a polynomial in X, this is of degree at most D. As a polynomial in Y, it's at most D. I mean, if I were to think as polynomial both X and Y, it could be a degree at most 2D. But point is, I don't have terms which are too high degree in X or Y. So, okay. And again, I'm going to pick this uniformly at random by just picking each of the coefficients uniformly at random. And I'm going to define the edges. So A is connected to B, and an edge if this polynomial vanishes at A comma. So this is my new graph. So let's see now. So now this graph now is symmetric between the two halves. So let's see that it does not contain KST, but S on the left and T on the right. And of course, the opposite would be the symmetric. Well, doesn't contain, we're saying doesn't contain, means it contains very few copies of that, and you can after deletion we again come back to the graph which contains no copies. So the key observation that if I have S vertices on the left. It's a distinct vertices on the left. Then, if I'm going to look at the polynomials in Y on the right hand side, which they induce, so if I then look at the polynomials, okay, let me just call them F1. So F1 of Y is the polynomial obtained by plugging A1 for X and similar, etc. So all these polynomials are Fs of Y. It's the result of Y. So this I get S polynomials, one for each point. So this polynomials in the Y variable. Now these are random polynomials, right? The randomness is basically inherent in the random choice of F. So these are S random polynomials, and these polynomials are mutually independent. So as a random variables, they are mutually independent random variables. Are independent random variables. Okay, and the reason the independent random variables is that remark which we made last lecture, that if so key to sealing this is that remark that if I have say g of y g of x, sorry, is a random polynomial, of degree at modulus d, and we have s distinct points, then the values of this polynomial are mutually independent. Mutually independent. I mean, under the conditions we wrote, so which is degree of the polynomials got to be bigger than the number of degree plus one must be bigger than this, and the Q choose 2 S choose 2 must be smaller than it. Okay, so if degree is large enough and the size of the field is, that was that remark which we made last lecture. And note that if I'm thinking of this polynomial f as a polynomial in x with coefficients being the polynomials in y, this is exactly that lemma, right? We can, or phrase it differently, I can just group together. You can just look at this the terms which have the same exponent of y. So apply this to f. We are writing it as the sum of alpha x with alpha, sum of beta c of beta. No, sorry, I want to be beta y to the beta, sorry, that way around. Y to the beta, alpha x to the alpha, right? So basically, I'm applying this thing inside here. It's just a random polynomial in x uniformly chosen of degree at most d. So I'm applying to this polynomial this observation, which says the coefficient of y to the beta is uniformly random, and this is all independent for different choices of a1. Okay, so and now we are basically doing the same. So what we have that these polynomials are independent, and therefore we can run the same argument. because in that argument, we did not use the points we chose here, well, independent. We only chose that they were S-wise independent. We only one thing we needed, when we look at S points, we were analyzing the common neighborhood, and for this we only need independence of this polynomials at those S points. We did not need a total independence. So same proof works. Okay. Okay, so that's basically how you can complete the proof for the extremal number. And one more comment, which is, since we already have everything on the board, it's worth making. We can also see what happens if we have if we want to get bigger t, even bigger than this argument, but maybe getting more edges. Okay, so let me just make it maybe that as a comment, because that's going to be okay. Let me just we can also modify this proof to get that word. So here is another theorem. Every S, there exists some T naught such that if you look at a larger T than this T naught, then the extremal number of the KST is bigger than some constant depending on just on S times T to the power 1 over S and to the power 1. Okay, and you might remember that in the Kovashov-Turan bound, we proved upper bound, the dependence on T was exactly the same. It was T to the power 1 over S. So, so this claims actually as T goes to infinity, dependence is indeed this. So Kovashov-Turan is sharp and also in that sense. Again, once T is large enough. Again, so as I told you, we don't know what to do when T is say it's compatible to S. This is open. So let me again sketch how to modify this proof. For that, it's again given what we've done, it's easy. So what we are going to do, we are going to pick a bunch of this, not one polynomial, we're going to pick a bunch of polynomials. So okay, so let's say K to be basically this. And again, I'm ignoring the floor sign. So if you want to be pedantic, include the floor here. So let K to be this, and we are going to pick now K polynomials. Or degree D in each of X and Y. So in other words, we're picking them exactly the same way we'll pick them over there, independently. And then we're making an edge if at least one of them vanishes. So in other words, we're taking just the union of the graphs like this, so just independently sample K graphs like this, and we take the union. If there exists I, so that F I K B is equal to 3. This is the construction. Since we're taking union of K random graphs, again, the size of a union will basically be K times size of each graph because intersections on average will be small. So this is lower bound is easy. And how we analyze it, whether we contain KST or not? Well, we are going to be asking, well, suppose I take my S vertices. So again, so I have some S vertices. Okay, A1, A2, AS. Am I interested now in I'm interested in the common neighborhood? Well, there will be several ways we can get neighbors. Well, for each edge coming from A1, it's in one of these K graphs. So we're going to choose which of the K graphs this edge is in. We're going to choose which of the K graphs this edge is in, and so forth. So there are going to be K to the S choices of which graphs there are. And for each of them, we're going to get a polynomial. We're going to get a polynomial again. So choices, and instead of we're going to get again S polynomials in Y, and these polynomials are going to be independent, because again, even if you chose the same graph in each time, it will be independent by what we said. And of course, if you pick different ones, its choices are independent, it's going to be independent. Okay, I'm not writing, but it's clear. We're going to get it, and so probability is going to be the same. So our probability of failure, so number of edges to remove is an expectation is at most that quantity q to the s squared s d to the s q to the minus d minus 1, and now we're going to multiply it by k to the s. Okay, but this is tiny because my k is no more than q, right? So I'm multiplying by at most q to the s squared, and d my already was 2 times s squared. It will kill it still. This is so tiny that even if I multiply by this, it's still tiny. Okay. So same thing, same argument works, and the neighborhood will become a neighborhood will be just union of all the common neighborhoods, right? So it'll be same size as before, but times k to the s. So and that's it. K to the s is t. So that's basically how you can modify to get the sharpness of the Covary Shorsh-Turan. Again, question?
Why can't we choose more than K polynomials here? Where does it?
Oh, no, because what's the size of common neighborhood?
Of course, yeah. You just
The
have,
common neighborhood is that for each of these K to S choices, I have d to the neighborhood of size d to the s. And then I'm multiplying, so neighborhood will have this size.
I see.
Right?
Yeah, gotcha.
D is constant, it's like about 2s
Right.
squared. But this will,
So still nothing goes wrong. It's just a problem that.
yeah, so this union bound is,
That
there's a huge
union-
amount of
yeah.
huge room to spare here. It's
That's
it's
when
here.
in the typical case, you're gonna get something. Gotcha.
I don't understand this K to the S. Are you assuming edges incident to a vertex on the left, all coming from the same?
No, I'm saying look at the so okay, maybe I should let me write and make anything there. Okay, so pick say I1 through IS, so each of these are so I'm picking which polynomials I'm choosing. So which polynomial I'm using for the first vertex, second S vertex. And then I'm looking at the F I1 of A1. I'm looking at F of I2 of A2. I'm looking at F of IS AS. Okay. So I'm looking at this, oh, sorry, comma Y. Y, comma Y. Right, this is right.
So what I'm saying is, could it be that there's a KST where the edge is incident to A1 coming from two different points?
Yeah, of course. Did I mess it up a little bit? Um,
If we color the edges.
yes. You are totally right. Give me a second. I do understand what you're saying. Let me think for a sec. No, it's fine. No, this is exactly, sorry. Thank you for confusing me. So then I can unconfuse everybody. Okay, right. It's sure. So let me draw a picture. I have the first vertex, second vertex, third vertex. Okay. Now each vertex on the right has a type. What's the type of the vertex? It's what are the colors of the edges going to A1, A2, A3, and so forth. Okay. There's a type, which is basically this which graph this edge in, which graph this edge in, and which graph this edge in. Okay. So the right hand this KST is now cut into chunks, right? Depending on the type of the vertex. Okay. Okay. There are K to the S possible types. Okay.
I see.
K to the S possible types, and I'm bounding the size of each of the chunks of particular type. Okay, and the way I'm bounding it is as before. I'm just looking. This is on my type. I know if this is type, I1 through IS, which is I'm basically looking at the polynomials. Okay, I1 through IS related at appropriate vertices. Again, this is still independent. And so same argument as before. It tells me that this is at most D to the power S. So this is at most D to the power S. So the total size of the neighborhood is at most D to the S times K to the S. This is just a constant depending on S. So I mean, this is not mattering for what we're doing now, and that's all. Does it? Good. All right.
Yeah, okay.
All right. So this is okay. So let me, given the time we've got, I think I will. I was thinking. Okay, I don't think I'll. Yeah. Okay. I can do another application, but probably I won't get in 10 minutes. So I can try saying a couple of words instead. Again, just on a level of SketchUp, how one can improve this bound. So what people feel like they want. Quick other application, maybe we're running 5 minutes over time, or just hand wavy, how can improve this bound by using more algebraic geometry. But again, it will be very hand wavy. Any people.
What's the another application?
Another application. Okay.
No, I mean, what's that?
I was planning to do the box problem, so the extremal number for the K2222. So here is, let me advertise that application. You can see it or not. So here is okay. So now we're talking about D-uniform hypergraphs rather than graphs. Same kind of we define similar quantity, but again, now this is F is some kind of D uniform hypergraph. And the story there is very similar to, well, somewhat similar to the story for the graphs. If F is so uniform, so we will take say F is a uniform. So now if F is D-partight, then again you have a covariant Sturan bound of this minus something positive, and again this positive depends on that. Okay, shows much like covariant. And the proof is basically the same as covariant Sturan. You just need to induct on D. That's all. Okay, so the simplest case of this is when F is K2. Okay. I will basically just abbreviate this by K2 because I just writing this is pain. So I just want to know that again, this is so it's not very challenging to modify this kind of argument to show analog of the where one of these numbers is very large compared to the rest. Okay, similar kind of ideas, and it's not this thing, however, is kind of surprising because we can actually do some kind of similar random algebraic construction because for Bezout, we actually going to have something large. So it's a nice twist on this random algebraic construction. So so let me tell you what probabilistic gives you. So this is easy. Maybe I should not call it theorem. It's exercise by nowadays. So this is probabilistic method, vanilla. It basically it will tell you to do the calculations. This is at least n to the power d minus d. Okay, I don't want to lie to you. This exponent. So again, so the probabilistic argument will tell you this. The upper bound, which you're going to get from generalizing covariant Sturan, is using its 1 over 2 to the d minus 1. So it's a basically factor of d difference. And as usual, improving on main probabilistic construction is hard, and so there is improvement. Okay, let me just get mess up if I don't look it up. The theorem. So if R it's a natural number, I think it's guys. D as R and S, sorry, R as natural numbers satisfy D minus satisfy ds minus 1 to d minus 1 R. Then the extremal number of this is at least constant the power n minus d r over this. In particular, if we take r to be 1, then we can just take to s to be the floor of the ratio of this ratio. We're going to get x and d is bigger than n to the power d 1 dividing by the ceiling of 2 to the d minus 1 d. So this is strictly better than, because previous pure probabilistic bound is the same but without the ceiling function. So this is a strictly better bound than pure probabilistic.
So we cannot use the ceiling for this thing.
Right?
Nice.
So I'm saying, oh, this is a statement. I'm saying this statement is already better than basic probabilistic
Yeah, yes.
because even if you choose r equals 1. Okay. Of course, you can optimize this r for particular value of s. From particular value of t, I'm sorry. Okay, so let's see a proof of this. So we are going to mimic the construction of the K2 free graph. Remember, we should basically obtain basically we're taking inner product of products on left and other side. We have a plane here, plane there. We take inner product. So this was basically linear in each of the two coordinates. So it was linear in the left side and linear on the right side. We're going to do the same thing, but we're going to choose equations randomly. Okay, so let me tell you what the construction will look like. And then we will need to analyze it.
Boris, so I think it's expect the number of verses to be like.
Analyze by one slide. I'm just deleting all the edges from the one. But if you want to add what's the same argument. So construction will be d-partite. So again, much like for the graphs, our constructions will be bipartite. This will be d-partite because this is d-uniform hypergraphs. So d-parts. D-parts. Each part will be a copy of S-dimensional vector space over FQ. So, and again, we will choose a polynomial to define our hyperedges. Tell you what this is. So, we're doing this check. We will pick some t. Okay, I'll tell you what t is in a moment. Pick t that is linear in each of the axes. And we'll do it at random. Among all such. Maps. Again, over a Q.
So each xi is the element of the S.
Yeah, so the xi, yeah, so the xi is again as a vector. Right, xi, x, right? This is the variable. So x1 is a variable referring to the this set, x2 is one referring to this set, and so this is what we're going to do. We are figuring and trying to model such maps. And the equation, so the A1, A2 up to each of these x of the x of the correct. Okay. And this thing is an edge, hyper edge, if t is equal to 1 at this point. So if you remember our construction for the K2 free graphs, it's exactly the same, except here we're going to pick a random multilinear map rather than a specific one. And that's really all. Right, so it should, for t equals to 2, we could pick any non-degenerate bilinear map. You know, doesn't have to be inner product. Here we're going to take a random. Okay, and so let me prove or maybe sketch, because I mean, given we are running over time, I probably leave a couple of manipulations and exercises. Let me sketch why this construction works. Again, and we're going to delete bad facts. We're going to delete one edges from bad facts, as usual. Except it will be twisted, and I'll tell you what the twist is. So what will happen? The first step 1, the expected number of edges before deletion is exactly what you expect. Namely, there are going to be q to the s to the power d ways to choose one vertex from each, right? And probability. I'm sorry. It's an edge. I will pick. So I will expanding r equals 1 as thing. We are going to pick a bunch of these guys in general case. We are going to pick r many of these equations. Again, r equals 1 case is one, which is, already gives us improvement. More generally, we can pick r of them, and we are basically all of this must be true in general case. But again, if you just want to think about a single equation, it's already, it's not going to make a difference. So probability we have probability that a given tuple is an edge is going to be probability that each of these guys vanishes, 1 over q, so 1 q to the power minus. So this is the first step. The second step.
So do you want to be that number should be 0 or so t should be
1. I want 1. It's no, it won't be 0. The second thing, which is slightly harder than the first thing, is that the expected number of the bad configuration, the K2 Ds before deletion, is again also going to be exactly what you expect. There is, so it's going to be q how many you're going to expect? Well, you're going to pick two vortices from each of these parts. And so it's q to the s times 2d, right? And how many edges are there? There are going to be 2 to the d edges. So this is not surprising. You're getting exactly as many as you expect. Okay, you're getting exactly as many as you expect. Let me maybe, since this is harder than this, and again, and actually this one even implies this, let me maybe tell you how to prove this second bullet point. So the way proof works is the following. So let's fix some 2 vortices from the first part, 2 vortices from the second part, and so forth. So I'm picking, say, the A1, 1, A1, 2, A2, 1, A2, 2, etc. And finally I'll pick some point A D1, A D2. So I pick two D points to fix A11, A12, A21, A22, all of that are AD1, AD2. So this is a bunch of points. And I want to count what's probability that all of these are edges. Well, I'm going to again and see which one should I go here. So I fix that, and then I can I can find linear transformations. Okay, lying to slightly. I'm sure somebody will tell me, Boris, you're doing something illegal now. But okay, wait me to write what I'm doing before you tell me this. I find linear transformations, which will take these points to the standard basis vectors. So I can change. So in each of the copies of the S-dimensional vector space, I can change my coordinate system so that the first vector goes to the first basis vector, and the second one goes to the second one. Okay, it's just linear change of transformation. And then it just becomes a question like, what's the probability that I pick around a random bilinear map, which is basically which yields this particular standard basis vectors to 1. Okay, and it's easy to check for any way you want to define your linear transformation on the standard basis vectors. This is such a multilinear map, and there everything is uniform. Okay. Okay, and if now I think I feel you raising hands for saying something illegal. Anybody? I think Ben.
I'm just concerned that these are not related to the TI.
Notation. Yes.
Thank
you.
Distracted by that. Now trying to find what you're doing.
Notation wise, yes, you are totally right. Right.
So you want to count the possibility that we cannot bend essentially.
No, but this is basically the analogous to the step which we did before about first changing coordinates, so the x1 first coordinates of our vectors will be distinct. I'm saying I'm changing my coordinate system so that my first vector is first basis vector, my second vector is my second basis vector, and in the first in here, and again, this is my first basis vector, second basis vector, first, so the second one. And then basically you can just check for this easy choice that probability is first. Again, this is basically, it's the only thing I'm lying to you is in order to find this linear transformation, I need these vectors to be non-collinear. But if they're collinear, you cannot have that T is equal to 1 on both of them, because they are going to be a scalar multiple of one another. That is non-zero scalar multiple. So this is basically the only trick which you need in order to do this. So point is, for now, everything looks like the usual probabilistic construction, right? Remember I told you the probabilistic construction gives you a bed bound, and we're trying to improve it. So far, everything looks exactly like vanilla probabilistic construction, right? Expected a number of edges is what you expect, because it will be, and this everything is going to expect. It's based on your edge density. So nothing. We have not improved anything yet. The key observation here is linearity. That let me just write it. Let me write it here. So key observation is that if A1, 1, and A1, 2, etc. Gives us a copy of K2D, right? So again, so this is in the first F Q to the S, and then there is the A D1, A D2. This is in the D F Q S. Then any linear extrapolation of this also gives us a copy of F2D. So then if I take say F A11, and this is the A12 prime, again, A 21, let's say A2 prime, etc. So again, I'm replacing these ones by some new things. A D1, A D2 prime, where A1, so AI2 prime is is on the line, so is on the line joining the A1, the appropriate points before. So it's on the line joining I1 and I2. So picture, so maybe bigger picture. So I have this thing. There is A11 here, A12 here, and there are a bunch of vortices here. I look at the line passing through them. If I replace the A12 by any point on this line, the value of T will not change because T is linear. And so, and it takes value 1 here and 1 here. So it's going to take one value 1 here as well. Similarly, I draw a line from in here. Then again, I replace this point by this. Again, value of T is not going to change. So there are going to be a huge number of copies of the this forbidden graph, which all share the same A11, A12, A21, etc., AD1, sharing the same edge. So if I delete that edge, I'm killing not a single copy of K2D. I'm killing all of these copies at the same time. This is where I'm winning over the usual probabilistic argument. So, deleting edge AY1, A1, A21, etc., AD1 yields Q to the power D copies of K2D. And this is where you win, and this is where you're going to get. Okay, this is outlined in the sketch. Okay, so as I promised, I run over time. I told you this would be over time sketch application, and I think I should stop lest nobody shows up tomorrow being tired and disappointed. Okay, thank you.